Alright, today we are going to be talking about section 5.7 and 6.7. Both are dealing with regular polygons. One of them is working with kind of our angle measures and seeing what happens there. And then the other one is going to be talking about symmetry and kind of what types of symmetry we have within our regular polygons and kind of where those lines of symmetry are located. So let's go ahead and get started with our learning target here. So our learning target for today is to be able to find the lines of symmetry and where they are, and then talk about the interior angles of regular polygons as well. So we're going to start with three sum theorems here. They tell us what the angles in each of our shapes should add up to be. We already know the first two. We've talked about the second one a little bit. But for sure the first one, we talked about this one before. The triangle sum theorem says that the angles in a triangle add up to be 180 degrees. If I then take two triangles, and they don't have to be the same triangles, but I put them together, that's going to give me a quadrilateral. So if I take the two 180s and combine them together, that gives me 360. So for a triangle, our sum is 180 degrees. For a quadrilateral, our sum is 360 degrees. Yeah, and you can abbreviate those if you would like those definitions. The one that we're more concerned with, though, today is our polygon sum theorem. This is one that I'm hoping you found using that worksheet that we talked about last week after your quiz. You were working on this. But hopefully you got to it. If you did not, I'm about to give you that equation here. Anyways, okay? So right here at the bottom, this is our theorem. Okay, this equation here is n minus 2 times 180 degrees. So the n here is talking about the number of sides. Okay, and then we would subtract 2 from that, multiply it by 180. That's going to give us the sum for all of the angles in that shape. This actually works both for a quadrilateral and a triangle as well. If we would plug 3 in for n for the triangle, we would get 1 in the parentheses there. 1 times 180 is just 180. If I plug in 4, I get a 2. 2 times 180 gives me the 360 for a quadrilateral. Okay, so this actually works for the shapes that we already know. Okay, let's go ahead and start to apply this theorem, though, and this equation as we start to look at some problems that we can do and we could have done for a while, but they're in a little bit of a different format, and so we're going to talk about those now. Okay. These problems are what we call our ratio problems. So instead of telling you one of the angles and saying find the other ones, what I'm going to tell you is how the angles are related to each other. And so I'm going to give you this ratio here. That's what's right up here where it says 1, 2, and 3. That tells us that those angles have a relationship such that whatever one angle is, that's going to be kind of one unit or one thing. The next one is going to be 2 of those things, and the last one's going to be 3 of those things. Well, you can even start to see by the way I'm saying things, we don't know what that is. And so we can actually create that as a variable, and we know what all 3 of them have to add up to be. So if I think of the one thing, well, that's a 1, and a thing we're just going to call an x. I need to add to that 2 of those things for that second angle, and 3 of those things for the third angle. Okay, and that 1, 2, and 3 are coming directly here from that ratio. It's nothing to do with we have 3 angles, it's just the ratio that they give us. Okay, and we know if we're adding those all together, if we're in a triangle, those have to add up to be 180. So if I keep going here, I'm going to have to combine my like terms on the left side here. That's going to give me 6 x's, gives us 180 degrees. Okay, I can then take and divide by 6. If I divide 180 by 6, I get x is equal to 30. Okay, now x is equal to 30 doesn't actually tell us anything about our angles, because this up here, our ratio and kind of how we set up our equation, is really my angles. And so when I'm looking, my angles are actually going to be 1x, 2x, and 3x. So I need to know what all 3 of those are. Well, 1x, that's really the same thing as x, so that one actually is the 30, but we won't always have a 1 there. We'll look at an example here in a minute. That's something else. 2x, that's going to be 2 times 30, so that's 60. And 3 times 30, that one's going to actually be 90. Okay. If we look here, there is a little bit of a difference. We're asking for A, B, and C, so we do kind of have to decide which one each of these are. We can use the fact that the smallest angle is across on the smallest side. So if I take the smallest side here and kind of go back, that's going to be angle A. So 30 is going to be angle A. 60 is going to be kind of the middle side. That's going to be angle B. And 90, that's going to be our biggest side, which is angle C. Okay, so we can actually work at this problem. If I just showed you the work for this problem, you'd probably think it was similar to what we were doing before. The real difference, again, is just what we're starting with up there at the top with with that ratio. Okay, so I'm going to go ahead and clear this one off and start to look at our problem here, which asks us to find the sum of the interior angles of both a pentagon and a hexagon. Okay, so we have the pentagon over here on the left. I want to know what all those angles in there add up to be. Well, if I think of a pentagon, that has 5 sides. And I know an equation that can tell me what the sum of all these interior angles are. Again, that equation is n minus 2, that's a minus there, times 180. Okay, I apologize, it's hard to write with this program I'm using. But we're going to go ahead, so that's 180 degrees. If I'm looking for a pentagon, that means I'm plugging 5 in for n. So that's 5 minus 2 times 180. Okay, well, 5 minus 2, that's 3 times 180. And 3 times 80, or 180. If I then look, well, 3 times 1, that's 300. 3 times 8 gives me an extra 24. So that's actually going to be 540. This is going to be our total for a pentagon. Okay. And again, you can use a calculator there. Right now I actually don't have a calculator by me, so I just did that one in my head, but you can go ahead and use a calculator on these. Okay, let's go ahead and look at our hexagon. Hexagons have 6 sides, so instead of plugging in 5, I'm going to plug in 6. So we'll do 6 minus 2, we'll multiply that by 180, and 6 minus 2 gives me a 4 times 180. That's going to give me 400 plus an extra 320, that's going to give me 720 degrees. And that's going to be my answer for a hexagon. Okay, and that's for all of the angles added together. So if I look at all of these angles on the inside here, all 6 of them, that's all of these angles added together have to be 720 degrees. Okay, and that's for any hexagon. As long as it's convex, that'll still work. Okay, let's go here and look at another ratio problem. This time we're going to look at a quadrilateral though. Okay, first of all, we know that quadrilaterals are going to add up to 360 degrees. So it's going to be very similar to my triangle problem I did for number 1, but now we're going to equal 360 degrees instead of 180. Then I'm going to also have to use this ratio up here. Again, I have 2, 3, and 4, so that's my ratio of all of my angles, but those are really just groups of things. So really all I'm going to do is I'm going to take it, I'm going to tack x's in between all of those. So I have 2x, I'm going to add that to a 3x, add that to a 4x, and add that to a 6x. Okay, that's going to give us all of our pieces. I can now add all of those together. So if I combine all my like terms on the left side there, I have 2x and 3x gives me 5x, plus 4x is 9x, plus 6x gives me 15 x's, and that's going to equal 360 degrees. I can then go ahead and divide by 15 on both sides, and I happen to just know this one. That gives me that x is equal to 24 degrees. And again, you could use a calculator there. You don't necessarily need to know that off the top of your head, but that's going to be 24 degrees for x. Okay? But if I look here, I want to know what the angle measures are. I don't care what x is. I want to know what each of these chunks here in my first equation actually represent. So I need to find 2x, 3x, 4x, and 6x. Okay? So if I start with 2x, well, 2x would be 2 times 24, gives me 48 degrees. 3x, that's going to be tacking on another 24, which is going to give me 72 degrees. 4x, that's another 24, that's going to be 96 degrees. And finally 6x, that's an extra 2 24s, or an extra 48. That's going to give me 144 degrees. So if I look, those 4 angles are my 4 angles in my quadrilateral. If I want to do a quick check here, I could just add all of these together. They are going to actually add up to give me 360 degrees, which is what I need. Alright, we have one more here. We want to give the sum of the measures of a convex octagon. Okay, first thing we need to know is how many sides are in an octagon. Well, that's kind of like octopus, that's 8 sides. So that means I'm taking my equation, I have 8 minus 2, I'm multiplying that by 180, which is really going to be a 6 times 180. Okay, now I can kind of break that down. That's going to be 6 plus 480, looks to be 1080 to me. And you can double check that. Again, I'm not using a calculator, so if that's wrong, I apologize, but I believe it is 1080. 80 or 1080 degrees. Okay, and that would be the sum in an octagon. Okay, so just using that equation, as long as we know that, we're good to go. Alright, let's go ahead and move over into the next section. So this is on the back of your page. We're going to start to look at a regular polygon. We've actually talked about this definition before because we've needed it before now. But now we're actually in the section where we can kind of talk about what it does and what it helps us with. So a regular polygon is just a convex polygon whose angles are all congruent and sides are also all congruent. Okay, so both sides and angles are congruent. If we look, I've given you examples of kind of our first five, not necessarily our first five, but five of our regular polygons. We've talked about an equilateral triangle, okay, because that has all equal sides and all equal angles. That's the same. Square is kind of our quadrilateral example of a regular polygon because I have all those equal sides and all equal angles being 90-degree angles. Pentagon and hexagon, these ones don't have special names other than we would just call it a regular pentagon and a regular hexagon. Same thing with an octagon. I skipped heptagon here just because it's kind of a weird shape. We're more likely to see a hexagon or an octagon over a heptagon, so just throw that one in there. Okay. The next two words we have here actually go together. So we have equilateral and equal angular. We've also talked about these ones before. That first part of both of those words, the equa part of it, is just referring to equal. Lateral is actually talking about the sides, and angular is talking about the angles. So all goes in here. An equilateral is a polygon that has all the sides that are congruent. An equal angular is where all the angles are congruent. Okay, and if I really look, these two pieces here are more or less combining together to become our regular definition. Okay, so if we're talking about a regular polygon, and some people actually define it this way, a regular polygon is just an equilateral and an equal angular polygon kind of at the same time. Okay, let's talk about symmetry. So symmetry is kind of the big one from this particular lesson. And again, we're kind of combining two together, but symmetry is the big one that we're going to talk about here. And it really depends on how many sides our shape has. So if we start to look at this definition here, we're going to say that every regular n-gon possesses this type of symmetry. We have two pieces to it, but n here is again referring to the number of sides. That's a pretty standard thing in geometry. Whenever we have an n, that's referring to the number of sides in any of our shapes. So just be aware of that whenever you see an n-gon, that's for n sides, where we don't know the number of sides. Okay. So here are our two types of symmetries. We have talked about both of these before. We have rotational symmetry and we have our reflection symmetry, kind of over symmetry lines. And so number one here says that we have n symmetry lines, or those lines of reflection, that map the same part of the shape onto itself. So I can flip right over that and I get the exact same shape. Okay, and we'll have n of those. Those positions are actually going to change depending on if n is an even number or an odd number. We'll talk about those below here in the example, but let's go ahead and talk about number 2 first. Number 2 says here that we have n-fold rotational symmetry. That rotational symmetry is, again, I can spin it 360 degrees, and how many times does that shape actually land on itself? And that's the n-fold part of it. Okay, it's going to be exactly the same number of sides that it has. Okay, and this is all assuming that we have a regular shape too. If we start to talk about quadrilaterals in different shapes, they don't always have 4, but we're talking just regular here, so just the square. Okay, so let's talk about the rotational piece first, and kind of why this makes sense. So on the rotational piece, what I'm doing is I'm actually taking each kind of vertex here where all my my sides are coming together, and I'm going to rotate it to where the next corner is. Okay, that's going to give me one fold rotation. Then I'm going to take that one and move it to the next one, to the next one, to the next one, to the next one. And you can see that I could actually do 5 separate rotations there. And that would give me my 5-fold rotational symmetry in my pentagon, because again, I have 5 sides there. Same thing in the hexagon. I'm not going to draw this one, but you can kind of think of taking each point and moving it to the next one. And I would have 6 of those kind of movements all the way around before I got back to where I started. So that's where the rotational symmetry piece is coming from. I'm going to go ahead and clear my screen so we can talk about the rotational part. Alright, so probably the easiest one here on the pentagon is to see that we go straight, my picture, we go straight down the middle there. That's going to be our first line of reflection. Okay, and if we notice here, that's actually two types of reflection there as well. I'm actually bisecting this angle at the top, and I'd have a perpendicular bisector to the side here at the bottom. Okay, so this is both an angle bisector and a perpendicular, sorry, that's our perpendicular symbol there. Can't get them to connect, there we go. A perpendicular bisector. Okay, so the same line is actually both of those. And I actually have 5 of them. If I take and kind of think about my shape just spinning, I would have one going there, one going through each of my angles here, through each of my angles, and directly across the side from it. And you can kind of see here they all actually meet in the middle here. If I was drawing this on paper with a ruler, you would see that these actually all line up. But that point there in the middle is actually what we call the center of our shape. Okay, in a circle that kind of makes sense. Everything goes right through the middle. Same thing here with our regular polygons. Okay, let's go ahead and jump over to the hexagon now. This one's a little bit different. If I think about taking and splitting this one directly down the middle, going vertically right now, pretend like that went through the middle. Sorry about that. In our pentagon, that would both split an angle and a side. This one here actually only split angles. So I have separate angle bisectors. Sorry, I'm writing down the side there, ran out of room. So we have angle bisectors, and I actually have 3 of those because I have 3 pairs of angles that are directly across from each other. But I also need to have n totals lines of symmetry, so I have to have more than that. If I switch to a different color here, we can actually think if I go straight side to side here horizontally, I have one there, also have one here, and I have one here. That's more or less the other half of the lines I had here. Those are the perpendicular, the wrong way, perpendicular bisectors as well. So we have both types of bisectors. We have our angle bisectors and our perpendicular bisectors. Here they're separate lines in our even numbers or our hexagon. When we get to an odd number, those are actually the same line. Okay, it splits one angle and one side. And you'll get used to that kind of as we go. But the big thing here is we always have n lines of symmetry. So if I have 5 sides, I have to have 5 lines. If I have 6 sides, I have to have 6 lines. So we have to find all of those. Okay, so let's go ahead and start to look at these. If we look at number 1 here, we want to find the number of n-fold rotations in a regular heptagon. So a heptagon, remember that's 7 sides. I actually have this shape here. And so we can think about if I take A and move it to B, that counts as 1 fold rotation because I'm going to align everything else up on itself again. Then I can move A, that's now at B, to C. I can move it to D, I can move it to E, F, and G. I can actually move it 7 times around before I get back to itself. Okay, so this would have a 7-fold rotational symmetry. If we start to look at lines of symmetry, okay, this is an odd number, so I should have lines that are both a angle bisector and a perpendicular bisector. Again, I apologize, these are not going to be perfect because I'm drawing them on my iPad and not on a piece of paper. They're a little bit harder to do here. The big thing is we need to make sure we get all 7. Ooh, that last one's terrible. Let me try that one again. We do need to get all 7 on there. And again, they should all meet at a point in the middle if you're doing them perfectly. They might not all be perfect, but they should be close. Okay, and that point in the middle, again, is what we call the center. You'll need that when you get to your homework, I believe. Alright, let's look at this bottom part. So the bottom part is asking us to find the measure of just a single interior angle for a regular octagon and a regular decagon. Okay, if we start to think about a regular octagon and what we talked about in the last section, we know what the sum of a regular octagon should be, but we don't necessarily know what just one angle is. So that's what we're going to have to find here. Alright, so if we look at this octagon, first thing we need to figure out is what all of them need to add up to be. And again, that's going to use our equation 8 minus 2 times 180. And we figured this out on our last page. This is going to give us 6 times 180, which gives us 1080 or 1080 for our total sum in an octagon. Okay. If I then want to split that between all of my angles. I know that if I have 8 sides, I also have 8 angles. So I need to split that sum, 1080, and divide it by 8. If I do that, that's going to tell me an angle in a regular octagon is going to have to be 135. Okay? And that's, of course, assuming that we're regular, meaning that all of those angles have to be the same. If it's not regular, we can't do this part of it, because we don't know if I take some away from one and add it to another. I don't know how much I'm moving around between my angles to change those up. Second part here, we have a regular decagon. Decagons, again, have 10 sides. So if I start with my formula, this is going to be 10 minus 2. And I'm going to multiply that by 180. That's going to give me 8 times 180. I'm going to go ahead and do that here real quick. Gives me 1440. Okay, so 1440. I'm then going to take that and I need to split it across all 10 of my angles. So I'm going to go ahead and divide that by 10. When I do that, I get that each of my angle measures is going to be 144 degrees. So now, we can start to see as I take more sides and kind of add them in, our angles get bigger, which makes sense because as I start to add more sides, I get closer and closer to a circle where my angle measures don't really even exist anymore. They're so big that I don't actually have that difference. Okay? So as we add more sides, our angle measure should be growing and kind of getting bigger as we go. Alright. That is actually it for our notes today. So hopefully at this point we can now find all those lines of symmetry and look at those interior angles and know and find those interior angles of a regular polygon, either the sum or individual angles depending on what we're looking at. Okay, so your homework tonight is going to be from 5.7 and 6.7, but it's going to be a worksheet. So you can go ahead and fill that out. Make sure you have that finished for tomorrow, and I will hopefully be back and we'll go over that tomorrow morning.